Hi again everyone, Chris Tisdell here. In this presentation I'm going to continue my series of videos on differential equations, and I'm going to show you why solutions to second order ordinary differential equations with some initial conditions, why those solutions are unique. In other words, in this presentation I'm going to show you why there is one and only one solution to certain initial value problems. Now, this is a really deep question, and a lot of the textbooks and the presentations that I've seen really skip over the question of uniqueness. But in this presentation, we're going to prove that there is one and only one solution to these famous initial value problems. So let me share my screen with you, and we'll get underway. Okay, so the question is, why are solutions to linear initial value problems unique? In other words, why is there one and only one solution to a problem like this one? So this is a basic second order, a linear homogeneous differential equation coupled with some initial conditions. Here the coefficients A, B, and C are constants. A is non-zero. The alpha and the beta are also constants, and this is a very famous kind of problem that you see in science, maths, and engineering courses. The example that I've sort of mentioned here is in vibrating systems. So you've got a spring mass and damper system, and here x of t is the position of the object from its equilibrium position at time t. A here would be the mass of the object. B would be some sort of constant associated with the damping. So that the larger B is, the stronger the damping force. And the C here would be the spring constant. So a large value of C means a stiff spring. Okay, so you'd see this kind of problem in, say, a first course in differential equations, or maybe a second course in calculus. Now, most people, after completing a first course in differential equations or a second course in calculus, hopefully know how to solve this kind of problem. You form a special quadratic or polynomial type equation associated with the coefficients of these of x double prime, x prime, and x. You factorize, or you solve this, and you analyze the roots. If the roots are real and equal, then the general solution to this problem is a certain type. If the roots to this are real and unequal, then there's another type of general solution. And if the roots to this equation are complex, then there's another form of solution to this general problem. And then what you do is you incorporate the initial conditions and you refine the solution, okay? And what you end up with is one solution. But the question that I'm going to discuss in this presentation is the following. How do you know that the solution you compute when you run through this method, how do you know that that's the only solution? That's a very, very deep question. Okay, and I would claim that introductory books and YouTube videos on the subject really don't discuss this idea. So that's what I wanted to discuss today. I wanted to fill in a little gap, and hopefully you find it really interesting. So here is the result that I'm going to share with you today. This initial value problem, or IVP, with a second order linear ODE, constant coefficients, some initial conditions, A is non-zero. This problem has one and only one solution. Okay, let me just fix up my document camera for a second. Okay, just stay with me. Okay, let me just reshare that. Okay, sorry about that, it just froze for a second. All right, so here's the proof. We are going to assume that two solutions to this problem exist. And let's call the first solution y and the second solution z, and they'd be functions of t. And I'm going to let r be the function of t that is represented by the difference of these two solutions. What we're going to do is show that this function r of t is identically equal to 0. What does that mean? It means that y and z must be identically equal. In other words, they are one and the same solution. So the only way that two solutions can exist is actually if they're the same solution, so they're not two distinct solutions. Okay, so I'm going to do this in a number of steps. The first step I'm going to, first claim I'm going to make is that this function r satisfies the same homogeneous differential equation and also homogeneous initial conditions. Okay, so that's not a, it's not super tricky to show that, but I'm going to run through the proof anyway, and then I'll get into the slightly more deeper steps. Okay, so all I need to do to verify this claim is show that R satisfies that, that, and that. Okay. All right, so AR double prime plus BR prime plus CR equals the following. Okay, it's A y minus Z double prime plus B y minus Z all primed plus C y minus Z. Okay, and I want to show that this equals 0. Well, if I expand these brackets, remembering that the derivative is a linear operator, then I have the following. Okay, now if I team up the y double prime with the y prime and the y, I'll get the following. And if I team up the z double prime with the z prime and the z, then I'll also get the following. I can take a common minus sign out the front. Okay, now remember we've assumed that y and z are solutions to this problem. So that means that's 0, because of the 0 there, and that's 0. So what does this mean? It means that this equals 0. That's exactly what we wanted to show. All right, now let's show that the initial conditions are satisfied. So R of 0 equals y of 0 minus z of 0. So y of 0, because it's a solution to this problem, is alpha. Z of 0, because it's also a solution to this problem, is also alpha. So obviously that becomes 0. And R dash of 0, well, that's just from here. If I differentiate and plug in 0, I'll get y dash or y prime of 0 minus z dash or z prime of 0. Because y and z satisfy this, you know that that's beta and that's beta, and so their difference will be 0. So hence, star hold. So R satisfies this special homogeneous problem. Now you might think, why is that important? Well, we'll get to that in the next part of the proof. Okay, so we've shown that R, the difference of any two solutions to this problem, satisfies this homogeneous or homogeneous problem. Okay, we'll come back to that in a minute. I'm going to introduce a new function related to the function r. So u of t is defined by this. It's r of basically r squared plus r of t, r dash all squared. Okay, now firstly, because we've got the sum of squares here, this function u is always non-negative. And if I can show that u is identically equal to 0, then r is 0 and r dash is 0. Okay, now remember what we're trying to do here is show that r is identically equal to 0, and that way any two solutions must be the same, one and the same solution. Okay, so from my definition of u, I see that it's always greater than or equal to 0, and the second claim I'm going to make, and the final claim, is that u is less than or equal to 0. So if u is greater than or equal to 0 and less than or equal to 0, u has to be identically equal to 0. Okay, so that means that r is identically equal to 0. And then I've actually proved my result, because that's what I'm trying to show. Okay, so let's consider this function u, and let's consider the derivative of u with respect to t. Okay. Okay, so I'm differentiating products here, and I can either use the product rule or the chain rule, and essentially I'll get the following. Now I'm going to drop the argument of t off just to save a little bit of space. Okay, so this is what I get. Okay, so I've just dropped the argument off just to save a bit of space. Now, if I take absolute values on here and transfer that over here, I'll get the following. Now, if I use a triangle inequality, this is the following. Okay. Now I know that r double dash satisfies this equation because I proved that claim before. So I can rearrange this equation and get r double dash or r double prime in terms of lower order derivatives. So if I rearrange the differential equation in star, I'll get the following. Okay. So okay, so if I expand this out now, I'll get the following. And again, I'm going to use the triangle inequality here. So that, if I do the triangle inequality on that, I'll get something like the following. I'll get r dash squared, and this times this will give me something like the following. Okay, so now I've got an r dash squared, and I'm kind of left with, sorry, let me fix that up. Okay, that's better. So I've got an r dash squared here, and I can try to work on these things. So let me just bring those together. Okay. So now what I would like to do is actually work on this here. Now I can use a little inequality there, which I'll just sort of tuck in down here. It's the following: 2CD is always less than or equal to C squared plus D squared. So what I'm going to do, I'm going to apply this inequality to this, because then I'm going to get something involving R squared and R prime squared. Now it's not clear how that's going to help us, but it will become clear in a minute. Okay, just let me get some more paper. Okay, so if I continue this on now, I'm going to apply this inequality in here. So I'm going to get R squared plus R prime squared plus this. Okay, so where to now? Well, I can write this in the following way. Okay, what I'm going to do is try to team up this with this, and you'll see what I mean in a minute. If I form a big constant out the front, say, let's write it like this. Then I've now got something, an inequality, on the absolute value of this derivative involving R squared and plus R dash or R prime squared. Now remember, U is defined in terms of R squared plus R dash squared, right? Exactly that. So if I write that in terms of U, then you'll see that something quite magical happens. Okay, so let me just write this out a little bit more. Now, if I let, say, K be this big mess here, then I'm going to get what's known as some differential inequalities. So we have formed the differential inequalities. Okay, let me just move that up. So that's U there, so this. Okay, now I'm using inequalities here because we'll actually expand this and form two inequalities. Okay, so you may be looking at this and going, well, so what? This is very important. Okay, this will allow us to do stuff. Now, based on our definition of U, what do we have an initial condition associated with this problem? Well, we do. R and R dash satisfy this and this. So what would U of 0 be? It would be 0 squared plus 0 squared, which is 0. So we don't have a differential equation here. We have a differential inequality, which is a first order differential inequality and some initial condition. Now, believe it or not, that's enough for us to solve the problem. Okay? Let me show you what I mean. we have, so if I just expand this a little bit, I get the following. All right. Now remember what I'm trying to do here. I know from my definition of U, it's always non-negative. I'm trying to show that U is also non-positive. Okay, so that's what I'm really trying to achieve here with these kind of differential inequalities. So let's see if we can do that. And you would solve these things, and I use solve in the very loose sense, the same way you would solve any first order differential equation, ordinary differential equation. You would use an integrating factor. Okay, so let's discuss that, and we almost finished the proof now. So let's take the right-hand inequality, and let's rearrange it, and let's multiply through by the usual integrating factor. Okay, so the integrating factor for this one would be something like e to the negative kt. Okay, now we know from, oh, my screen has just frozen again. Let me just reshare that. Okay, we're back. All right, so we know that the left-hand side of this inequality is the derivative of a special product. Okay, and it's the u times the integrating factor. Okay, so for say t greater than or equal to 0, we integrate both sides of this from 0 to t to form the following. Okay, so let's just change to the dummy variable s now. Okay, if I integrate this, it's still left-hand side still less than or equal to 0. And I know the fundamental theorem of calculus tells me that basically I'm taking the integral of a derivative, and so that's just the difference of the function evaluated at the limit points, or the limits of integration. Now, when t equals 0, I'll get u of 0 here on e to the 0. What's u of 0? U of 0 is 0. So that'll disappear, and then I've got u of t times something that's non-negative is less than or equal to 0. So what does it mean? It means that this has to be less than or equal to 0. That disappears. That's always positive. This product is non-negative, so that has got to be less than or equal to 0. So for t greater than or equal to 0, I've kind of achieved half of what I wanted here. We've shown that this is true for t greater than or equal to 0. Okay, fantastic. So now what we want to do is show that the same inequality holds for all t less than or equal to 0. Okay, so up here I use the right-hand inequality. Let's use the left-hand inequality and work on the case t is less than or equal to 0. Sorry. Here we go. Okay, so you follow the same steps, except your integrating factor is not going to be e to the negative kt, it'll be e to the positive kt. Okay. All right, so that will compress to the derivative. Okay, my screen's just gone again. Okay, all right, so we get the following. All right, so now if I integrate in the following fashion, for t less than or equal to 0, we integrate from t to 0. Okay, so you integrate both sides of this from t to 0. Okay, again, use the fundamental theorem of calculus. And over here, you're going to get something like this. Now, what is this? This is 0, okay, from over here. Okay, u of 0 is 0. So that'll disappear, and then I've got this times this negated, or negative, is greater than or equal to 0. What does it mean? It means that u, and remember this is positive, and so u of t is less than or equal to 0 for all t less than or equal to 0. So we have shown that u is less than or equal to 0 on the positive real axis. We've shown that u is less than or equal to 0 on the negative real axis. So we've actually fulfilled our claim now. We've shown that u is less than or equal to 0 on the whole real line. Okay, so we spent a lot of time doing that, but we're pretty happy about it. Okay, so let's get back to our claim. We've claimed that u is less than or equal to 0 on the whole line. We just proved it using some differential inequalities, and the fact that u is greater than or equal to 0 tells us that u is identically equal to 0. So what does that mean? It means that r must be identically equal to 0. So any two solutions to this problem must be the same solution. Okay, so let me just write that down. So any two solutions must be one and the same solution. So what does this mean? And we're getting very close to the end now. It means that when you solve a problem like this, say in a spring damper mass problem, and you find one solution, it must be the only solution. It must be the only solution. Thus, solutions to 3 are unique. Okay. So that is it. That is it. That is the proof for why solutions to these basic initial value problems are unique. That's why there's one and only one solution to these kinds of problems. Now, on physical grounds, we would expect there to be one and only one solution to the problem. Okay, if there was no solution at all, well, your equations wouldn't be a very good model because the spring mass damping system would still vibrate and move. Okay, if we repeated the experiment with exactly the same initial displacement, initial velocity, and the same A, B, and C, we would expect the solution or the behavior to be identical. Okay, so that's one reason why we would expect unique solutions. But here is a mathematical proof. Okay, quite a long one, but I hope you enjoyed it. Now, these kind of differential inequalities that we were playing with down here, say here and in here, are related to a mathematician called Gronwall. And Gronwall proved a result involving differential inequalities about 100 years ago. So in mathematical terms, these kind of methods are not that old. Anyway, what do you think of my solution or my proof to this problem? It's a pretty deep question, the question of uniqueness of solutions. And textbooks and lots of presentations on YouTube, they kind of ignore the question of uniqueness. You compute a solution to a differential equation or initial value problem. Of course it's the only one. Well, why? Why is it the only one? That's what I've hoped to get you thinking about with this presentation, and what I hope that I've shed some light on for you with this little class. So let me know what you think. If you have any comments, any questions, if there's any videos you'd like me to do, post them in the comment section below. Thanks for watching, and your feedback, your suggestions are always welcome. All right, thanks again.